Welcome back to calculus. Excuse me. Today we're looking at section 8.5, integration tables. So integration tables can be found in the back of most calculus textbooks, including the one that we are using for our course. And learning to use them is kind of straightforward, but it also has a few little quirks to it. The most important thing is make sure that you have a perfect match. Okay. Sometimes the formula for the integration will have a minus sign in it, and you have a plus sign, and that definitely changes it. So make sure you have the right one. All right. So I have two examples on the board. We're going to go through 5 examples total. The first two are really pretty straightforward. So the first one is just the integral of dx over x times the square root of x plus 4. Now in our textbook, that's number 29, part A, and where our A is 1 because there is a coefficient on A, and our B is the 4. And using that and just substituting in all the A's and B's, we get that it's 1 over the square root of 4 times natural log of this wonderful absolute value of the square root of 1 times x plus 4 minus the square root of 4 all over the square root of 1 times x plus 4 plus the square root of 4 plus c. Cleaning it up, basically just changing all those square roots of 4s into 2's, we have our answer. So that was pretty straightforward. We didn't have to do anything weird with it. This one's also not too bad. We have the integral of e to the negative 3t sine of 4t dt. Now, we can do this using some really fun integration by parts, or we can use the table in the back with a negative 3, b 4, and number 114. So doing that then, plugging everything in, we get e to the negative 3t all over negative 3 squared plus 4 squared. And when you clean this up, I didn't feel like rewriting it. Just turn it into 9 plus 16 and get 25 there. But then the rest of it is just negative 3 sine 4t minus 4 cosine 4t plus c. So there we go. 2 pretty nice examples. Let's go and get some more. Okay, so this one's pretty fun. I have the integral of x squared plus 6x all over x squared plus 3 squared. Now, unfortunately, we have to make some pretty big changes to this before we can actually start integrating. So I did it ahead of time, and I didn't put it down on the board because this problem already takes up the whole board. But what we're doing here is I'm using partial fractions. So if you need a reminder on how to do partial fractions, please go back and watch my video on section 8.4, and you can see it there. So when I did the partial fractions, I was able to split this up into 3 integrals. Integral of dx over x squared plus 3, plus the integral of 6x over the x squared plus 3 squared dx, minus the integral of 3 over x squared plus 3 squared dx. And you can see my answer here. I have it all written out. It's just 1 over the square root of 3 times the tangent inverse of x over the square root of 3 minus 3 over x squared plus 3 minus x over 2 times x squared plus 3 plus 1 over 2 times the square root of 3 cubed times the tangent inverse of x over the square root of 3 plus c. And you're probably asking yourself, where did all that come from? Well, that's everything over there. And so let's go take a look at that. So what I did is I went off to the side and I did each of these pieces separately, and I just needed a place to write the answer, so it's already there. So let's move this computer just a little bit so that hopefully we can see what we're looking at. Yes. All right. All set. So here we go. The first integral is that integral of dx over x squared plus 3. Well, that's straight out of number 17 in our book, with a being the square root of 3. If we do that, we can very quickly just get that it's 1 over the square root of 3 times the tangent inverse of x over the square root of 3. All right, the second one is a little bit more fun. Actually, I really like the second one because it's just a basic substitution. If we let u be x squared plus 3, du is 2x dx. So what that means is I still need a 3 because of the 6, right? 2 times 3 would be 6. So I have 3 times the integral of u to the negative second. And so if we integrate that, we get a negative 3 because we're going to add 1, which gives us negative 1. Turn that into a negative 3. and we get negative 3 over u, or because we had u to the negative first, and so I just put the u back in, x squared plus 3. And so there's our first two parts of that massive answer that we had for that last problem. Finally, we have this one, the integral of 3 over x squared plus 3 squared dx. This is number 33 in our book, with a being the square root of 3. And again, just plugging in all the numbers, we get negative 3x over 2 times 3 times x squared plus 3 plus 1 over 2 times the square root of 3 cubed times the tangent inverse of x over the square root of 3. And of course, I did a little bit of cleaning up back over there. These 3's cancel, so I just get a minus x over 2 times x squared plus 3. And that's where I got that answer over there. So that one was big. It was enormous. You had to be able to do partial fractions. You had to be able to pull out a couple of different formulas from the back. Loads of fun. So let me get some more stuff on the board. Okay, so here's my fourth example. This one isn't nearly as bad as that last one, but the last one's big again, so I thought I'd just throw this one on the board without anything else. So we have the integral of cosine inverse of the square root of x over the square root of x dx. Easiest way to do this one, although there was a formula that I was able to find doing some fun things with powers, but the easiest way to do this one really is to just recognize that if you let the square root of x be u, that when you take its derivative, you get 1 over 2 times the square root of x dx. And so we can do a substitution, and the square root on the bottom just drops out very nicely, and we're left with the integral of 2 cosine inverse of u du. And then using formula number 104, with a being 1, we get that this is 2u cosine inverse of u minus 1 over 1 times the square root of 1 minus 1 squared u squared plus c. So we plug back in our square root of x for all those u's there, and if you square a square root, you just get the x. So there we go. That one's pretty nice. All right, one more example. It's actually not horrible, but it's bigger. All right, so our last example is a power reduction for a cosine function. So we did these back in section 8.2. We did this kind of thing, but we can also do it using the formula. Now the trick here is that we're going to have to do it twice. So I have the integral of 8 cosine to the fourth 2 pi t dt. So that fits in very nicely to number 68, with a being the 2 pi and n being the 4. So I really brought the 8 out front, and then just the integral. And so for the integral, you can see I filled in all the information. Cosine cubed 2 pi x sine 2 pi x all over 4 times 2 pi plus 4 minus 1 over 4 times the integral of cosine squared 2 pi x dx. And right there, we run into the fun bit with these power reduction formulas. I have another integral. I'm going to have to do this again. So I cleaned it up. I still have the 8 out front of everything. But you can see I did the multiplication, got 8 pi here. I did the subtraction to get 3 over 4. And now this second integral is actually number 66 in our book, with a being 2 pi. So if I do that, still the 8 out front, still have this mess here, plus 3/4 now times what this formula gave me, which is x over 2 plus the sine of 2 times 2 pi x, and all over 4 times 2 pi with our plus c on the end. Cleaning it up, multiplying everything through by 8. The 8 cancels here to leave the pi. 4 times 2 is 8, so that gets rid of the 8 as well, leaving this with just the 3x. And actually, here we have an 8 pi times 4, but I used that 8 to cancel this one, and so that's why I have just 4 pi. So there we go. There's the mess of our answer. You can see it. Sometimes people will go a little bit farther here and break down this 4 pi and turn it into sines and cosines with that 2 pi x like we had with everything else. And I changed to x. I should not have done that. I was using t. I'm not changing that for you, but that's why we ended up with x instead of t, because somebody was a dummy when he wrote down the problem on the board and switched to x. So there you go. Enjoy. Have a great day.